Hey everyone, it's me, Steve. It is November 6, 2018. It is voting day here in the States, so if you haven't done that, please go out and do that. But that aside, welcome to another Geo-Files episode. I said I probably wasn't going to do another one. Well, I'm doing one. And this is about ternary diagrams and classification of igneous rocks, which I mentioned in my previous video. So I'm going to go into those here, okay? Now, why am I doing it here and not in the office with all the geo maps and everything? Well, because Lilith, my one-eyed kitty, she lost her eye when I moved into this house a year and a half ago due to a bad infection. She now lives in that room. She is a great cat. I love her to death. She's this little skinny thing. She is 11 years old now. But her problem is she's an alpha, and she does not get along with Blackie and Bela. She got along with Ezra and Katan most of her life because she grew up with them. But when Blackie and Bela came into the picture, she started peeing and pooping all over things. And since she's been isolated, she was in the basement and she loved it, but I couldn't keep her down there anymore. I felt bad. So I brought her up here. And as long as she's isolated, she's fine. She's happy isolated. It's so bizarre. Okay, so ternary diagrams and classifying igneous rocks. This classification system was actually compiled by this guy here. This photo of him, Albert Strickinson, I believe is how it's pronounced, is online in public forums and stuff, so I'm assuming the photo is free game, as it probably is since it's on social media. But anything you see herein is going to be of my creation, unless I say otherwise. I will mention if something is not mine. And at the very end, I'm going to show you some pictures and examples of rocks in the field. And throughout the video, I'm going to hold some rocks and show you how they are that I have here. I don't have all examples of all these rocks I'm going to show you, but I have a few that are readily accessible. I have a lot more in storage, but a few that are accessible. Okay, this book here is sort of like the Bible of how to classify igneous rocks. And Albert had his hand in this. He is no longer with us, but in 1991 he wrote this paper, which is free online. You can feel free to get it, and this was kind of what started most of this. This paper, though, only includes what we're going to talk about. There's basically two types of ternary diagrams we're going to talk about here. We're going to talk about one for Plutonic and one for volcanic rocks. The Plutonic one is in here. There's these three charts for pyroclastic rocks and things like that, and other exceptions. We are not going to touch on these at all. These triangles. We are going to concentrate on the double triangle diagrams. Okay, so what you're seeing here is a diagram from Wikipedia, and this is Plutonic rocks. And like I said, I love the diagram. The author's name is in the corner. This diagram is great, but it's for Plutonic rocks, and those triangle diagrams only, it doesn't have volcanics on it. But it's a really pretty looking diagram too, so I just thought I'd show you that, that example there. Okay, now I'm going to talk about the actual plots themselves. You're going to have, in each of these diagrams, you have two triangles, one like this and one like this, and they're joined to each other. Well, we're going to talk about the top part first. For Plutonic rocks, what you're seeing here is, I believe that's Ezra behind me, but other than that, what you're seeing here is the triangle. QAPF diagram is what we're drawing here, but right now we're just dealing with the QAP. Q is quartz, A is alkali feldspar, and P is plagioclase. You're going to plot relative percents. We're going to do the F's here in a minute, but before we can do the F's, I want you to see the numbers here are the percentages. And as you can see, like quartz at top, that would be 100% quartz. If you had 100% alkali feldspar, you'd be here. If you had 100% plagioclase, you'd be here. The alkali feldspar decreases, plagioclase increases, and vice versa. So your 10, 35, 65, and 90 there would be from alkali feldspar to plagioclase. But if you're going from plagioclase to alkali feldspar, the 90 would be 10, the 10 would be 90, the 65 would be 35, and the 35 would be 65. So it would go from one to the other. It just depends on how you're doing this, because this is not going to be done from 3 points like a USDA ternary diagram. I need to make that clear. You're only going to plot 2 points. It's actually a lot simpler to use, and you don't really need to compute much to do it. The only thing you have to remember is if you have less than 90% mafic minerals, well, what are your mafics? Well, your mafics will be the dark minerals. But when you calculate this QAPF diagram, you do not include things like the biotite, the muscovite, the hornblende, the amphibolite, any of that. You remove it from the rock. But anyway, so you have to remove those and readjust your percentages. Like say your rock is 15% hornblende, you need to pull that hornblende out and then recalibrate your 85% as 100. And that's a simple calculation because you can just do it as a whole rock. But if you got 5%, if you're doing it from the whole 100%, but you've got 15% hornblende, that means you have 85% QAP. Now, if your Q is just 5%, you divide 5 by your 85 and then figure out your percent. It's not that difficult, but you need to remove those accessory minerals. And so what you're seeing here, now that I've shown you the numbers, I'm showing you what the rock names are. And that's the beauty of this chart, because based on these 3 components, well, soon to be 4, but I'll get into that in a second, your quartz, alkali feldspar, and your plagioclase, and this book here, you know, that I showed you in the beginning, that Igneous rock classification and glossary of terms, I suggest getting that if you plan on doing a lot of this, because it is worth the investment. I own the book, but I'm not showing you anything from inside of it because I don't want to get slapped with a copyright strike. So like these diagrams I'm showing you right now are mine. So here you can see you have quartz granite, granodiorite, tonalite, quartz cyanite, quartz monzonite, cyanite, blah, 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 etc., etc. And at the very top, you have a quartzolite. I have seen in my life one field example of a quartzolite, and I'm going to show it to you at the very end. But anyway, but if you look in the lower right here, you see things like diorite, gabbro, and anorthosite. There's 3 in one box. Well, what does that mean? How do you decide which is which? Well, determining the 3 can be somewhat ambiguous, but I'm going to talk about each one real quick. Anorthosite. Anorthosite is essentially a magma that is crystallized from pure plagioclase. It's generally going to be a very light color, if not white. It may have some accessories in it, like, you know, a little bit of, you know, hornblende or something like that. But it's going to have no quartz. But it will have a lot of times kind of this little luster to it that you get in labradorite, that translucence that you get in labradorite. And actually, labradorite is often in this, so you'll see these bluish hues to it. And the rock itself will usually look slightly bluish or grayish or white, or very pale gray or white. And it's not a very heavy rock. It's actually pretty light. It's not like a basalt or a biff or something. So it's very unique too in the fact that in the Precambrian anorthosites, like tonalites and granodiorites, are extremely common rocks. But unlike tonalites and granodiorites, anorthosite does not have a volcanic equivalent. This is the only rock on this diagram that does not have a volcanic equivalent. The beauty of the QAPF diagram is you have one for Plutonic and one for volcanic. Essentially, one for coarse-grained and one for fine-grained rocks. Ambiguous. The book that we use, that Igneous rocks classification, is a little bit ambiguous as to what is considered coarse-grained and what is considered fine-grained. It even gives a range, like from 1 millimeter to 3 millimeters. So depending on your discretion, you could be using the volcanic or you could be using the Plutonic one. And I actually talked about this in my Devil's Tower video because technically part of Devil's Tower is Plutonic and other parts are volcanic. So there are gray areas, okay? And there is some discretion here. But anyway, back to anorthosite. Anorthosite has no volcanic equivalent. We don't know of any surface flows of anorthosites or their fine-grained equivalent. We don't even have a name for them because they don't exist. We've never discovered them. All right. Every other rock you're going to see here, The Plutonic has a volcanic equivalent. The volcanic has a Plutonic equivalent. I'm going to talk about some of them, all right? And they'll plot in the same areas on the diagram as well. That's how you'll know if you have the equivalent or not. Okay, diorite. How can you tell diorite? Diorite looks a lot like anorthosite. Except it's lacking the labradorite, doesn't generally have that blue luster to it, and it tends to have a lot more heavier or darker minerals such as biotite and hornblende in it. And it is the plutonic version of andesite, which we're going to talk about andesite when we get to the volcanic part. But diorites are extremely common, and they tend to exist more in dikes and sills than they do as actual plutons, but there are some in existence. If you're in the field and you have doubt as to whether something is an anorthosite or a diorite, to err on the side of caution, you should pick diorite. That's more likely what it's going to be until you can do some actual chemical analysis with it. And that's, I think you can need, like, especially for plutonic rocks, you can pretty much use these charts in full. In the field. There's no reason to oversimplify it. I mean, there are times when things get a little bit ambiguous, or if they're from or to, they show, like if you're on a line between tonalite and granodiorite, you know, you could, you know, that in that case it would come in handy. Okay, now we're going to talk about gabbros. Gabbros, unlike anorthosites and unlike diorites, are real easy to tell in the field. They're essentially coarse-grained basalts. That's essentially what they are. Basalt would be the volcanic version of it. Right here is what I have, is a gabbro. They tend not to be light in color. They tend to be dark like this, and this is actually greenish gray. You probably can't tell from here. There's some minor accessory minerals in this. This particular gabbro has less than 1% quartz in it. It's a good hard gabbro. And the thing about it is it's heavy. Why? Because rocks like basalts and diabases, which we're not going to talk about, and gabbros, are mafic rocks. They have a lot of iron in them, and that makes them heavy. Iron's pretty heavy element. And orthosites and diorites are lacking in iron, giving them their lighter colors. And I'm going to touch a little bit on some of the other ones here before I move on to foids. You see tonalites or granodiorites. I mentioned that in the Precambrian, they're very common. Well, tonalites are excessively common up until the Neo-Archean. So before the Neo-Archean, we have almost exclusively tonalites and some granodiorites. There are almost no granites at all. True granites. They're not there. They just weren't forming. And that actually is a key to giving us the clue that modern plate tectonics was not in operation until the late Archean, at least, although it's probably a lot later than that. So now we get mostly granites dominate in plutons. I mean, we still get tonalites and granodiorites. They still occur, but we usually get granites now. And you can actually divide granites into two parts, a Monzo granite or an AF granite. I don't do that. I don't see the point of that. And in the field, it can be really hard to tell. So just the basic granite part is okay. Now we're going to touch on the cyanites. Cyanites are really common in the Keweenaw. Some of the Keweenaw dikes up in the UP in Ontario are almost all red cyanites, and hornblende will be the major constituent mineral or the accessory mineral in them. So you see these red rocks with big hornblende crystals. I actually have pictures of these things. I'm not going to show them to you here because they're in one of my books, and Anyway, so that Monzo and Monzonites are kind of in between the alkali feldspar granites and or the cyanites and the diorites. It's kind of in between there, and like I said, I'll show you how to plot something here in a little bit. Okay, let's move on. Let's add the F's, the foids. So what you're seeing here is the addition of the bottom part of the ternary diagram, making it the diamond shape. And here I have the numbers in order, just like I did on top, except they're pointing to the voids. Now voids will mean, like the F will be 100% voids. Why is this a double-edged ternary diagram? Well, because if you have quartz in a rock, you will not have any void minerals. It is a physical impossibility for quartz to form if voids are present, and vice versa. Voids will not form if quartz is present. And we usually concentrate on the top part because the vast majority of rocks are in that top part. Now the bottom part does happen, as we've seen before with Devil's Tower. And here are the names of the rocks. As you can see, it's basically just add void to something or in front of it, and to point out that it has void minerals and no quartz in it. So I think that's pretty much just all I'm going to add about that. And real quick, what I'm going to show you here is a field classification for plutonic rocks. This is the one I use. It's slightly different than the one that's in the Igneous classification book and different than the IUGS one. But I personally think this is a lot better. This works well for very weathered rocks and stuff like that. The granodiorite-tonalite is just a hyphenation I use, or you could just use granotonalite. You could use that too. So this is just what I use. Now I'm going to show you how to actually plot one of these on the plutonic. And then when I get to volcanics, I'm not going to show you again because it's the same process, just different names, all right? Okay, so back to our plutonic rock with names. Now, like I said, this is not like the USDA ternary soil classification. You're not using 3 points, you're using 2, because your alkali feldspar and your plagioclase, you can draw 2 lines, not 3, and find the intercept. Just 2 and find where they intercept at a single point. So you're going to have your alkali, remember, alkali feldspar is present at the expense of plagioclase and vice versa. So you're going to swing back and forth on that, and your line, the top of the line between the alkali feldspar and the plagioclase ratio, the top of the line is always going to intercept with the quartz, okay? And then it'll swing like a pendulum on that bottom, depending on how much alkali feldspar you have, how much plagioclase you have. So if you have, say, I don't know, we'll say 70% alkali feldspar, all right? Your line's going to be right about here, okay? And say you have 20% quartz. So your line's going to be right here. Okay, so you're going to have a quartz cyanite is what you're going to have. Okay, now it's right at the border. I just picked 20 because 20 forms a nice easy line. So it could be either a granite or quartz cyanite. I would go with the less common of the rocks, quartz cyanite, if it's just a hand specimen. But if I'm mapping a huge pluton and I get this one area that's a quartz cyanite and the rest is granite, I'm going to call it granite. All right. So if we were at, say, 90%, 95% plagioclase, all right, so here we swing it over to the plagioclase, there's our first line, and we are at 3% quartz, so our cross line is right here. We are in that diorite, gabbro, and anorthosite part. Well, if it's dark and heavy, it's a gabbro. I've already covered that. For the anorthosite and the diorite, like I said before, error on the side of caution. If you're unsure, pick diorite. And like I said, anorthosite will often have labradorite in it and have that translucent kind of luster to it that labradorite does. So if you see that, then you have anorthosite. And if you had your voids, you would do the exact same thing, except you'd flip it down and your F would become your intercept. The bottom, your F on your diagram would become your intercept instead of the Q. All right, so wherever your void line would cross with, so wherever your alkali feldspar plagioclase ratio falls relative to your void content, that's where you're going to draw your line, okay? It's the same process, just the bottom half of the diagram. So let's get into volcanic rocks here. Here I'm showing you the exact same thing as before. Here's your percents again, Q, A, and P. We'll do F again last like we did last time, okay? There's your numbers of percent. Same thing applies. Your ratios have not changed. It's the beauty of this. Whether it's plutonic or volcanic, the numbers don't change. The grain sizes do as to which chart you use, which, like I said before, is kind of somewhat ambiguous, especially when it comes to things like Devil's Tower, which could be plutonic or volcanic. So here's the names, okay? And as you can see here, you can see Rhyolite pretty much falls where granite does. Dacite would be your tonalites and granodiorites. Your trachytes are your AF cyanites. Your latites are your monzonites. So you can see that it's very similar. And those things all translate. And your basalt and andesite, well, basalt would be gabbro and plutonic, and andesite would be a diorite in plutonic. So you have equivalents. And notice there's only two. There's no third one because anorthosite has no volcanic equivalent. Please remember that. But if you notice, the top of the chart is naked. There's nothing written in there. Why? Quite honestly, because those rocks almost don't exist as volcanic rocks. Okay? And the reason being is like with the quartzolite and plutonic. Quartz is the last thing to crystallize according to Bone's reaction series. And here's Bone reaction series chart right here. Don't worry about the y-intercept, but you look at the bottom, you can see as a magma chamber cools from the top of the graph to the bottom, that quartz is the last mineral to form. All right? And if your magma is pure quartz and it's deep underground, it is going to become coarse grained by its very nature. Now, could this quartz magma erupt to the surface? It's possible, but we just don't see it. And so since we don't see it, we leave it off. Another reason why is if quartz is actually, if you were to have a lava flow on the surface and it was quartz, it would probably want to form larger crystals anyway because quartz crystallizes at lower temperatures. So as far as I can tell, that's the reason why there's nothing up there. Somebody else might give you a different answer, but... Okay, so I'm going to show you the volcanic version of a gabbro, which would be a basalt. I'm going to show you a special kind. Because since I'm in the UP a lot, the mid-continental rift basalts are almost always going to be what we call ambogoidal. Same thing with the andesites. I'll get into the basalt andesite difference in a minute, but here I want to show you this first. This is ambogoidal basalt. I got this when I was doing my Jacobsville paper back in 2016 and I visited Natural Wall Ravine. And even though those rocks are sedimentary, I found this lying out in the woods, cut like this. So what that probably means is some Michigan Tech student left it, either intentionally or unintentionally, on the ground, and I found it in Finders Keepers. But yeah, it's beautifully cut. And here's the rough side, and this is very typical of the basalts in the Upper Peninsula. Well, you might sit there and say, but these are coarse grain. Those are definitely more than 1 millimeter. So why is this a basalt? Well, this is different, okay? Ambogoidal, what these were is these little tiny dots in here. They're not dots, but minerals you see filled in here. What's up with those is those were gas bubbles, vesculars, okay? So when this magma cooled, it was full of air. And sometimes you'll even see vascular pipes near the top of lava flows. And that's a way to figure out if you're near a lava flow top or not, is to look for those pipes, because the gas could be less dense and the magma work its way out. When they don't work their way out, this is what happens, and eventually it fills in with minerals. And the minerals that filled in with this, there is some copper in this. It's disseminated, but it's in here. It's not native. I can show you something, and I am going to show you something with copper on it. But... and the white is pretty much calcite and quartz fill. And as you can see, a lot of it's secondary because there's a crack here. And this calcite's definitely secondary along that crack. So that's a basalt. I'm going to talk about andesites a bit here. Andesites and basalts can be hard to identify in the field. And quite honestly, the best way to do it would be color. Basalts tend to be gray and brown in color. Andesites tend to be purplish in color and slightly reddish. That's not a really good distinction, but it's the best way. Basalts also tend to be heavier. Like if you have a basalt of the exact same size next to an andesite of the exact same size, your basalt's going to be a little heavier because it's going to have a little more iron in it. So you can kind of gauge like that. And there's only one place really. Almost all the Mid-Continental Rift is basalt. There are some andesites. Copper Falls Park in Wisconsin has alternating basalt andesite flows. Okay, and quite honestly, that's how we gauge the difference as we look for the color between the two. Now you can always do a chemical analysis. And we use a TAS diagram for chemical analysis, but you only use this when you've actually run the analysis. It's not a field identification system. Okay, so andesite, what's that look like? Well, looks like this. You probably can't tell from the video very much, but it is purplish. I hope you can tell. But this sample has native copper on it. That orange color is all beautiful native copper. Let me try to focus on that a bit. You know, it's not really clearing up. Apologize for that. And the white is calcite. So this is an andesite. And it can easily be mistaken for basalt, especially in such a small specimen as this. But I know the bigger piece this came from. Okay. Now, rhyolites. Rhyolites are the volcanic equivalent of granites, and they're extremely common. They're extremely common in the Mid-Continental Rift. At the very end, I'm going to show you an in-place example of rhyolite, and they usually have phenocrysts in it. Phenocrysts are not the same as amygoidals. Phenocrysts actually form when the magma cools. As the magma erupts onto the surface and forms a lava flow, and it starts to crystallize, harden, become a solid. A lot of times these phenocrysts will form first and be related to Bones reaction series, and then the rest will quickly cool. Okay, and it can be really hard to pick out things like quartz in a rhyolite. How much quartz you have in it, because it could be the same color as the rhyolite itself. That being said, it's obviously possible. There is a porphyritic. If your phenocrysts are big enough and common enough, it's called porphyry. Okay. And there's a porphyritic rhyolite up in Mountain, Wisconsin, where I took my samples from that were getting those buckets. If you saw my video with those white buckets, I did not sample the rhyolite because that's already been done, and we know that's related to the Mid-Continental Rift. And that's a porphyritic rhyolite, okay? So, or rhyolite porphyry, if you will. Now, the IUGS standard does allow for divisions of rhyolites. Like up top here, they have what's called a quartz rhyodacite. And remember how I said that it's almost nothing in nature that we know of plots up there? Well, if it were to, this is what it would be. Okay, a quartz rhyodacite. All right. Now you can divide rhyolite and dacite. You see the red here in parentheses, so between those two red lines, you could call it a rhyodacite, or between the two black lines, instead of rhyolite, you could call it a liparite, but no one uses that word anymore. I don't know why it's still in the system, or it's still accepted. So those are other divisions of it that nobody really ever uses. I sure don't use it. If it's a rhyolite, it's a rhyolite. If it's a dacite, it's a dacite. No need to complicate things, especially in the field. Here's your bottom void part. It's exactly the same as a plutonic rock. All right. Here's your names. And like I said before, and then when I did my Devil's Tower one, the rock is traditionally a Devil's Tower, considered a phonolite, even though some of the crystals are huge, even throughout most of the rocks, so it should technically be plutonic. But it plots as a trachyte. There is some quartz in it, not very much, and sometimes there isn't. So at Devil's Tower, if you classify it volcanically, you're going to do a trachyte, a void-bearing trachyte, or a tephritic phonolite. Or if you use plutonic, it's going to be a syenite or a void-bearing cyanite, or a void monzocyanite. It's really up to you how you want to classify it. And what you see here is the field version that I would use if I was out in the field. My own personal preferences here, this is what I would use. And sometimes we get weird rocks. Like, I don't know, say you're on Ontario 129, I believe is the road between Champlain, Ontario, and Wawa, Ontario, that provincial route. And you pull off the side of the road and a rock that is mostly Plutonic, and you find something like this. This looks a lot like asphalt. Obviously it's not. You don't put glass in asphalt that big. And it came directly from the outcrop. What on earth is this thing? Well, there's big parts and there's microcrystalline ground mass. So is this volcanic? Is this plutonic? What is this thing? Is the QAPF even appropriate for this? Or does it fall into one of those triangular diagrams I'm not talking about? Well, at first, and I did a video on this rock where I actually counted crystals and percentages and did like areas to get exactly what this was, okay? At first I thought it was a lamb porphyry, all right? But this does have quartz in it, a lot of quartz. You just can't readily see it because it's gray, it's dark gray. So this is a quartz-rich rock. And most of the grains are over 3 millimeters, 1 to 3 millimeters in diameter. They're bigger than that. And you can see some have nice striations on them. This would be your plagioclase. So you clearly have a lot of plagioclase in this. There are some pink alkali feldspars. They're very far and in between. All right, it's a very low percentage of the rock. And I mean low, I mean less than 5%. Quartz makes up a significant part. And then you have this ground mass. Well, what is this thing here? This is probably represents a deep Pluton where you started to get a magma chamber where the magma started forming large crystals. And then as this thing, so it moved, sunk down because it's heavier now, it's denser, it's lost, because it's solid, so it sunk down. Parts started to remelt. All right, so the big crystals are becoming smaller, okay? And that now the magma has been around a lot longer and is starting to generally cool in and of itself, so you start to get this finer grained ground mass. And the quartz is all smaller grained. You don't see any quartz crystals this big. You don't even see any quartz crystals this big, okay? So that's likely what happened, is this formed higher in a magma chamber, forming large crystals that sank down as the magma had already started to begin cooling and became remixed. You can also see what looks like bake marks on the side of these larger crystals. That's likely what happened. That's just a hypothesis, though. I don't actually know. So what is this thing? I keep talking about it, but I haven't told you what it is. It's actually not that, it's a tonalite. That's what it is. It's just a very bizarre looking tonalite, but that's what it is. And it does plot on the upper half of the Plutonic QAPF diagram. And like I said, I've already done a video on it, and so I'm not going to do it again here, but it is a tonalite. Just a very weird looking one. Remember too, when we plot on these diagrams, we are dealing strictly with igneous rocks, okay? Igneous rocks that are directly derived from magma. We're not doing pyroclastic flows. We're not talking about ash flows. We're not talking about any of those. Those are different. These are directly cooled from magma. That's when you use the QAPF diagrams. There's a few exceptions, but generally it's going to be plot on that. And now I'm going to show you my gallery here of examples. Now, something I want to make clear before I start here. Here is an example of a dike. That orange pack is 10 inches in diameter, or in width, length, whatever, the widest part. This is a fine-grained rock, but it is intrusive. It formed underground, but we're going to classify it as volcanic, as if it had erupted on the surface, because of its small grain size. No grain sizes in here are more than 1 millimeter. You can't even tell with your eye any of the mineral makeup. And this is on Little Presque Isle in the UP in Marquette County, that island that we walked to. I've done videos on this before as well. And it's a basalt, Mesoproterozoic. And on either sides, we have gneissic tonalite, which has been dated to Neo-Archean. They have attempted to directly date the basalt dikes, but they have not yielded usable zircons. But all the other dikes in the area, some have been outside of the island, and they're all Mesoproterozoic. So those are assumed to be Mesoproterozoic. I did grab, there's a gabbro dike, and some of these dikes are kind of gabbro-like in the middle, coarser grained. And I did take some gabbro, and we are going to plan on having that dated so we can actually answer that question for sure. Now, what you see here, same orange pack in the middle, and I've talked about these, you've heard me drop this word a couple times, lamporphyrite. I'm not going to talk about them in detail here because that's a talk for another time, but this is also Little Presque Isle, and we have lamporphyry dike, which has been dated at Paleoproterozoic, surrounded by gneissic tonalite Neo-Archean. So lamporphyries are really cool rocks, and I will eventually do a video on them, just not right now, because they don't plot in a QAPF diagram. Okay, this is Little Mountain, and as you can see here, you can see a drill hole. This is a dike on Little Mountain in near Lance in Baraga County, and it's a quartz latite to dacite dike. Now, there's two major dikes on Little Mountain. Both are Mesoproterozoic. We know that for sure, and they cross one another. One is slightly magnetic and highly iron-rich. The other is not. This is the one that really isn't, and it's slightly more coarser grain than the other one. So that's an example of that. Unfortunately, this is the best picture I have. And this little guy here, this little hand sample here, under hand lens. This is from a lava flow. We know this was a surface flow from Mid-Continental Rift that's within the Copper Harbor conglomerate near Owl Creek. When I did my Copper Harbor paper, this is a very thin lava. There were a couple of tongues that intertonguing conglomerate that came off the main conglomerate body with a couple of tongues of lava. This is right when the Mid-Continental Rift lavas died out, or all but died out. You'll get the lakeshore traps further up, but this is where it started to die out. And this is an 8-foot flow, or an 8-foot thick flow, I think, if memory serves me. It's not very thick. It's never been mapped before. I saw this when I was out there and I did my map on it. I'll link it below if I can remember to do it so you can look at it. But you look at this, and this rock is very interesting. And it doesn't look like it, but it's likely a basalt. It's probably a mafic latite basalt. It could possibly be a sill, but it is likely a lava flow. And it's Mesoproterozoic. We know that for sure based on age relationships and dates of above and below rocks. Remember I talked about quartzolites? This is the only place on the planet I've ever seen one. It's also the only place I'm aware of that there is a significant one. This is Horse Race Rapids near Crystal Falls in the Upper Peninsula, in very near the Wisconsin border. Now you see this rock here? I have highlighted the quartzolite, and I think it's Mesoproterozoic. I do not know that for sure. It is surrounded by what is assumed to be metasedimentary Paleoproterozoic rocks, likely of the Michigami Formation. And why do I say assumed? Because they do not really resemble the Michigami. The Michigami tends to be dark, very dark gray to black. And here it's lighter colored green, highly metamorphosed. But more studying, this area is very poorly studied. It really is. I think there's like 3 papers max about anything that's ever been done in this area. So I will link this below too as well, the geo map of this. But this is a quartzite. It's really thick. It's too thick to be vein fill. All right, it can't be that. It has to be an igneous dike. And you look close, here is a quarter for scale. It's pure white quartz. And you can even see some of the crystals in it. So this thing's coarse grained. This is a plutonic quartzolite, and this is the only place I've ever seen this. Now, the Michigami further north will have quartz veins in it. Some of those may be igneous as well, but most are probably not. They're probably hydrothermal related. This is the only thing I am confident to say it was in place. This was when it was magma. It was a quartz magma that came up through the rock and solidified before it reached the surface. This is the only thing I've ever seen in the field where I'm confident enough to say that. This is a rhyolite. This is what a rhyolite looks like in the field. And this one has phenocrysts in it too and could be called porphyritic. This is a mid-continental rift rhyolite too. It looks a lot like the one at Mountain, Wisconsin, except that one isn't pink. That one, or is it red? It's more light yellowish brown. I'm not going to say the dreaded T word, tan, because tan isn't an actual color. But this is what a porphyritic rhyolite looks like, or rhyolite porphyry. Okay, now we have this here, and as you can see, there is snow on the ground. This was near Mass City in the UP. This rock right here, although it's surrounded by basalt, is technically a gabbro. This gabbro does have a little bit of quartz in it. You can tell by the white, but not all the white is quartz. A lot of it is plagioclase. I just wanted to show you a kind of lighter colored gabbro, unlike the one I showed you in hand specimen in the beginning, just so you know what it looks like. Now, this here, I love these. This is near, where was this, Steve? This is Marquette area somewhere. Maybe near Mesnard Mountain, if I remember correctly, which I don't think they call it that anymore. Anyway, this is a micaceous quartz monzonite, and it's what we call pegmatitic. Now, if you have coarse grains in a rhyolite, they're generally phenocrysts, and you call it porphyritic. Well, this whole thing, there's no fine ground mass here. This whole thing is coarse grained crystals, so it's a pegmatite. So you can add the word pegmatitic micaceous, or micaceous pegmatitic quartz monzonite would be the proper name of this, I guess. And you can tell it's micaceous because there's mica. You can see the mica flakes in this picture. They're so big. So that's what a pegmatite looks like, and stuff like this is real easy to classify in the field because it's just such a large coarse-grained pluton. This is one of my favorite outcrops. I love this outcrop. I do have a little paper I made below about this outcrop. If I remember to link it, I will. It'll be below. I hope I remember. But you see this dark rock with this pink rock? This is one of those things that's really awesome because what you have here, this is why structural geology and stratigraphy are closely related and intertwined, especially in petrology, where you get messes like this. You have these dark areas which are amphibolitic mylonites. Mylonites are highly metamorphosed rock that show deep internal structure. I'm not going to go into any detail on those here. It's a talk for another time. But that's what these rocks are. And then you see these pinkish stuff, this tonalite. And as you can see, I have Neo-Archean in question mark because that's likely what it is, but this outcrop has never been specifically dated. And I put Meso-Archean for the amphibolitic mylonite because it's never been directly dated and probably couldn't be either because it's so metamorphosed. But the reason why I assume that was older is because it has to be. Cross-cutting relationships here. This mylonite is clearly intruded by the tonalite. And the tonalite is a little finer grained here than in most tonalites. It's real close to that, well, is this a dacite or a tonalite line? But there's enough coarse crystals in it to make it a tonalite. This red line you see here in the corner, you'd have to actually look at the publication that I made to know that that's a fault, and you can see it because this is a zoom in of the most complex area I could find in the outcrop, but the outcrop itself is a big mess. And so that's what this is, and that's why when you are in the field, you need to not only know how to classify rocks, because these rocks are not in a box, and actually field relationships can make things a lot easier, or it can confuse things like this thing here. But you need to remember, you need to know stratigraphy is closely intertwined with structural geology, and if you're doing igneous rocks, with petrology. So you need to have a firm understanding of this kind of stuff. Before I wrap this up, I want to show you this chart here. This is also from Wikipedia, and so was the Bones Reaction series, I forgot to say that. But here you can kind of see, kind of like in a simpler diagram, if you will, SiO2 and volume of other minerals and where they would be in relationship to one another. That's what this chart is trying to explain here. And you have a volcanic and a plutonic, so you can know the equivalents, and notice there's no anorthosite on this chart. So you can kind of see how ratios exist in reality to one another. So if you have a rhyolite or a granite, you could have some muscovite, biotite, and amphibole, but it's not likely. You're probably not going to have those in the rock. But if you have a diorite, you could easily have a lot of amphibole and a little bit of biotite, but muscovite is almost not going to be in such a rock. And if you have basalt or gabbro, you're not going to have any amphibole, biotite, or muscovite. You're going to have pyroxenes with some plagioclase in it. You're going to have some calcium-rich plagioclase, I should say, in it. And you can see there's no quartz, unlike with granites, granodiorites, and rhyolites and dacites. You're not going to have quartz in those rocks, although from the QAPF diagram, you can have less than 10% or 5%. So, you know, you can have some quartz, but this is a general chart to show you the relationship. And then there's other stuff on here that I haven't talked about. Okay, so that's it. That's all I'm going to talk about here. Hopefully the next Geo-Files episode, as Lilith becomes more accustomed to that room and I put more stuff in there, because the complaint with the Devil's Tower video was there was a lot of echoing the sound. The sound was lower quality, that's why. I'd moved everything out of the room and you were hearing echoes. So I got to put some stuff in there to absorb some sound, and I'll start recording in there again, hopefully. And Lilith, you'll get to see little one-eyed Lilith, one-eyed Lily. You'll get to see her then. But anyway, that's it. If you have any questions or comments, please feel free to leave them below, and I hope you learned something.